welcome to Math World. Today we're going to talk about piecewise functions. Alright, piecewise functions are a little different than the other ones because they're kind of like a transformer in the fact that they take all the other functions and they push them together to make one super function. Alright, so let's see what that kind of looks like. We'll start with just a very simple linear function. So if I say f of x is equal to 2x plus 7, we know that's a linear function that starts at a y-intercept of 7 and goes up 2 over 1, up 2 over 1, a slope of 2, or down to back 1, to extend this line in the negative direction. All right, this is an increasing linear function. All right, now what's different about what we're going to be doing today is we're only going to take a piece of that function. We're not going to take the entire line. I graphed the entire line so you could see it, but really I only want to take a portion of this. So let's see if I can get a line on here and say, okay, well, I really only want this function from, let's say, from negative infinity until the point of about -2, right there. I only want that much of the function. In fact, the rest of the function I'm going to try to erase here. See if I can get rid of it all. Yeah, I don't really want any of that function. And so I'm only going to use a piece of this line. Now, the way we're going to show that with our equation is we're actually going to draw a little comma after the function, and then give the domain that we actually used this function. So in this case, we started from negative infinity, and we stopped when x was at -2. So really, anything that's less than -2 we'll use. When x is less than or even equal to -2, that will work for us. And I'm using -2, not the 3, because remember, we measure domain on the x-axis. So you can see I'm underlining the -2 here. That's when this function kind of stopped at -2. And so the way we write our piecewise functions is we always have our rule, our function rule, and then we have a comma, the domain in which we should be using that rule. And the reason we have to say that domain and rule is because we're going to have more than one rule. We're going to have more than one function here. All right, so there's my first linear function that tells me when x is less than -2, use this line 2x plus 7. I'm going to change my color here and create another function. And I'll use another linear one just to keep it simple. I'll say, okay, when f of x is, let's try -3x minus 3. Okay, so that tells us we should be starting at -3. I'm sorry, that's a +3. Starting at -3 because of the -3. And we should be going down 3 over 1, down 3 over 1. And of course, we can go backwards by going up 3, back 1. Up 3, back 1, and I could extend this further to the left, but I'm actually going to stop it right there because remember, I'm only using a piece of a function as I create this. So I'd like to create this second line that's going to actually start at that domain of -2 and extend all the way until, you know what, I'll stop it here at, looks like a +1, not -6, +1, because again, we're looking at the x values for the domain. So at what domain should I be using this piece of a linear, decreasing linear function? Well, I'll say, let's start at -2 again. Start at -2, and when x is greater than or equal to -2, you can use this line, which is this little -2 here. And then we're going to continue using it until this point here, which I stopped the line. So if I look up at the x value, I can see it's at +1. So when x is less than or equal to +1, you can use this green line. In fact, I'm going to need to erase that extra plot I made because I'm not using that part of the linear function. I'm only using a piece of it. I'm only using that green linear function from -2 on the domain x-axis until positive 1 on the domain x-axis. So I've got two pieces of a line, a red one and a green one, and the domain tells me when to use it. Now, the way they're going to write this function, they're not really going to have f of x show up more than once. In fact, they're only going to write f of x one time. So let's get rid of that. And the way they're going to show that this is all one function, not multiple functions, is they're going to put in brackets. So let's go ahead and change our color. And we'll see it more like something like this, where, hey, here's our piecewise function, f of x. And guess what? We're going to have multiple functions inside of it. So you can kind of see f of x is equal to these multiple rules, two rules now, that have two different domains of when to use the given rule. And let's throw in one more piece to this super function. Let's try, I'm going to use a straight line, a constant. It's very common for them to throw in constants. So remember, when we see a function such as like y equals -6, well, that's telling us to draw a straight line at y of -6. So I would draw an entire straight line across the graph like this at -6. But again, I'm not using that entire line. I only want a piece of it. So let's say I will start it, maybe let's just start it where the green one left off. Let's start it right here at an x value of -1. Let's make our line there, and I'll create a straight line so that we have a straight line here. So from x of 1, and we'll take this forever out of the graph. So there we go. It's a little crooked there, but you see that all those values are at -6. All right, now remember when we showed this equation in our function notation, the y is already kind of written here as the f of x, and our rule is just going to be -6. -6. It doesn't even have an x or any math involved for that matter. The rule is just, hey, -6 is the answer. And when do we use that? Well, we need to refer to a domain. And here, let me get my self out of here a little bit so I'm not in the way. Move me. All right. What domain should we be using this constant function of -6? Well, when did I start? I started at an x value of +1. Remember, we always look up at the x value of when domain is an x value. So when x was greater than or equal to +1, we use this rule of -6, this blue constant line. Let me get rid of this extra stuff. You know, I don't really need the y equals -6. That was just what it normally looks like by itself, because now I have this this piecewise function that's giving us all the pieces that we need written correctly. You can see here's the y portion, there's the rule, and there's when to use the rule. Okay, that's how we're going to show a piecewise function. Okay. Now, what's kind of interesting about this, not only does the rule look like three equations or three functions, and the graph looks like three pieces of a graph, you can see three lines here, we can also use it to evaluate the function. That means if I give you an x or y value, you can give me the corresponding x or y value based on our rules. So here's an example. If I said if x equals -6, well, then what would y equal? Well, there's two ways you can do this. One, you can look at your domain in our written function and say which one of these rule sets has x of -6. Is it when x is greater than 1? No, -6 isn't greater than 1. Is -6 between 1 and -2? No, it's not. It's actually the first one. When -6 is less than, -6 is less than -2, we would use this domain. There's your winning function. So if x is -6, use this rule. Use 2x plus 7. All right, so I'll actually go ahead and figure out that y should be equal to 2 times -6 instead of x, because x is -6, plus 7. All right, that would be, what's that, -12 plus 7. And -12 plus 7 is -5. So mathematically, if x is -6, according to this rule, y would be -5. Now we can also look at the graph to see that. If I look at x of -6 on the graph, well, if I walk over on the x-axis, I should see that at -6, I can walk down to the graph, and where does it hit the red line? It hits right here at a y value of -5. So you can see visually on the graph that that ordered pair, -6, -5, is the answer. If x is -6, y is -5. Now this works for any of these functions. So let's do one more. What if I said if, ooh, this yellow is a little weird, but I think you can see it. If x equals 8, what will y be? Well, I can look at the rules in my equations, or I can even just look at the graph. Well, if x is 8, that's over here. Let's walk down to our line and see that it would land right here on this blue line. When x is 8, y is -6. So that would be the answer. Interesting enough is that our last rule said that when x is greater than 1, the answer is -6, right? That means even if x was something like, I don't know, 100, 100, we can't see that on the graph, but we still know it's going to be -6 because our rule said whenever x is greater than 1, y must be -6. The answer to the function is -6. So you can use the equation even if it's off of the graph. The equation kind of is the main rule, and the graph is kind of just a visual representation of all of our rules. All right, so we just did 3 rules in 1. That is a piecewise function. If you have any questions about writing a piecewise function, graphing a piecewise function, or evaluating a piecewise function, please put those in the comments. All right, one last thing I do want to just point out, because I know it shows up pretty often. Let's see if I can bring this in here. Oh yeah, I got another graph. Let's see. Place the image. All right, sorry, let me get this graph's a little weird. It's okay. All right, so one last thing I want to point out is two things. One, all these piecewise functions, they don't have to just be linear. I gave you 3 linear ones to be nice. So maybe we have a linear function up until a certain point, and then we have a quadratic function up until a certain point. So you can have more than one function type, both linear and you can have both linear and a quadratic, or even an exponential or an absolute value. You can have more than one type. That's one thing that's a little interesting. The other thing that's interesting is that the functions don't always have to connect. You may have noticed I did not connect these 2 functions. In fact, there could be a little gap in between the 2 functions. And usually when there's a gap, what they'll do is they'll make one of the functions an open circle. You see I just made an open circle there? That's telling us that we should be using this linear function when x is less than, well, since this is a closed dot for the linear, we'll put the or equal to sign, and then this is at 2, right? So when x is less than 2 or equal to 2, because of the closed dot, use the linear function. Use the linear function. However, if x is greater than 2, use the quadratic function. But I didn't put a or equal to sign here below. I didn't put an equal to sign below the greater than sign because of that open circle. Open circle means greater than or less than, but not equal to. Now, the reason that's going to be important is, what if I asked you to evaluate if x equals 2? If x equals 2, what y value should we use? Well, at x of 2, I look up and I kind of looks like I run into the quadratic function and I run into the linear function. There's two options here. Well, the closed dot is the winner, the one that actually has the or equal to sign on it. So in this case, I would use an x of 6. I would use the linear function. So be careful when there's a gap in between two functions that you're using the closed dot as your answer. All right, that's it for piecewise functions, putting it all together, and I'll see you in class. Now for a word from our sponsor, Papercut Games. This week's game, the Duke. All right, so this is a chess-like game. It's really kind of neat, and it's almost like Chess 2.0. So here's the game board. It's a little smaller than chess, but very simple. And on your turn, you're going to pick out a piece from this bag. So unlike chess where everything starts on the field, this is full of all your pieces. And you might pull out different pieces that look like this. They're named, they'll say wizard, or maybe you get a knight. And then you put that piece on the game board. Now what's cool about this game is that each piece kind of tells you what it can do. So you see wizard can actually go, if you think about it, it's in the middle here, it can go anywhere around it. It can attack anywhere directly one space around it. This knight, you can see, can go forward or kind of behind it. It can stop people from flanking it. This seer, who has a scythe, can kind of go farther away but can't attack itself nearby. So that's kind of neat that the game tells you what pieces do and how they attack each other. But what's even cooler is that as you move it, it then flips and has different movement. So now in this mode, the seer you see can attack directly next to itself or in those far corners. So it has different, I guess, orientation. So the footman originally is very closed, and then when it moves, it can kind of strike further away. That adds a really neat element to the game of, as you move around, how they attack each other. The main point of the game is just to, knock each other out, and last one standing wins. But it is a really cool concept, and what I really like about it is there's also expansions. So I got this, there's a dragon piece you see here that you can play with, or a jester. They have the Three Musketeers, King Arthur, Merlin, Conan the Barbarian. There's lots of cool expansions that you can put into your bag that's essentially your army and play with. Well, that's it. That is the Duke. It is kind of difficult to find, but it's worth it. I'm Mr. Bigsby, and I approve this message.